As with any substance that can undergo reactions and undergo changes, stoichiometry will always be there. Gases are definitely no exception. Gases go through reactions quite often, and so there are a few things that we can rely on when it comes to stoichiometry involving gases. One of the things that's kind of nice is that there is this set value and set constant that we can use called the molar volume when you have these two specific conditions set. It says that when a gas is held at 1 atmosphere specifically and 0 degrees Celsius, right, these two values, then it's defined where a mole of gas, 1 mole of gas, will occupy 22.4 liters of volume. Now, as you can imagine, whenever you establish these things where two things are set equivalent to each other, that's also going to be a useful conversion factor. So 22.4 liters per mole. Right, now that's a terrible way of writing that, but effectively that's the conversion factor that you would use. So anytime you have this condition of 1 atmosphere and also 0 degrees Celsius, that is considered to be a relationship that you can rely on. 22.4 liters per 1 mole. Commit that to memory. This relationship is known as the molar volume, which kind of makes sense because it's talking about how many liters there are per 1 mole, just in the same way that molar mass is how many grams there are per 1 mole. In this case, we're talking about gases, and this is specifically known as a molar volume when the conditions are set at STP, also known as standard temperature and pressure, STP. So this 22.4 liters of 1 mole, per 1 mole anyway, is only valid for STP conditions. And so you oftentimes have this definition of STP. Anytime you're not at STP, though, anytime you don't have 0 degrees Celsius or the 1 atmosphere pressure, then you cannot use that relationship. And this is, of course, true for an ideal gas. We discussed this before. Where ideal, of course, is this theoretical construct. So you can see on the right here that these are actually real gases, oxygen, nitrogen, hydrogen, and so on and so forth, where the volume, held at STP at the specific pressure of 1 atmosphere, will show you that these volumes are pretty close to 22.4. Not exactly, they're pretty close, but again, that's the idea behind this. So this is true for ideal gases, and again, we treat everything in this lesson, or especially in this section, as an ideal gas. Here we go. Example number 1. A sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of N2 are present in this volume? So again, you see the magic phrase STP. You also can see that specifically as 0 degrees Celsius or even 273 K. And then that's at 1 atmosphere. So that's assumed to be present. So you know that's available. How many moles of N2 are present? So some of you might be thinking, okay, well, we have a volume, we have a temperature, we have a pressure. We can probably use PV equals nRT. But again, one of the magical things about this is that once we identify it as STP, we know that the molar volume relationship is valid. So at this point, I can make the work even simpler and just say 1.75 liters of N2, right? That's the nitrogen gas. I know that for every 22.4 liters of that gas, it will be equivalent to 1 mole of that gas. This way, a really quick calculation will give you 0.781 moles of N2 is present in this sample. And this is kind of nice because you don't have to go through plugging in all these numbers anymore, right, for PV equals nRT, and instead just apply this relationship of 22.4 liters per 1 mole. Again, make sure you recognize, though, you have to have conditions set at STP. Example 2, a sample of methane contains 22.4 liters of gas at 25 degrees Celsius and 1 atmosphere pressure. How many moles of methane are in this sample? Well, okay, looking at this, notice that, again, your conditions are at STP, right? Not quite. Remember, this 25 degrees Celsius isn't exactly at STP. Remember, it has to be 0 degrees Celsius. So you can't really just use 25 degrees Celsius and assume 22.4. Furthermore, this is kind of misleading right here. 22.4 liters of gas. That magic number that you see, you're like, okay, just 22.4, that's all you have to know. But, of course, it has to be STP. So at this point, you cannot do molar volume, right, because we're not at STP. So 22.4 liters per mole, I can't just say the answer here is 1 mole. Instead, I have to go through and do the work. PV equals N times R times T. So then you plug in the numbers as appropriate, and then you solve for N. Turns out the mole amount of PV equals, or the mole amount of methane in this container is actually pretty close. It's 0.916 moles. So it's kind of close to 1 mole, but it's not exactly because 25 degrees Celsius is not exactly 0. Right, so you got to be careful about those. Now, beyond that, though, right, what if we have situations where we don't have things at STP? We saw one example of that case, but also do note that, we do have a lot of gases involved. One of the things that's important to recognize, though, is that anytime you have gases, there's a potential that you can form solids and liquids as a result of the reaction, but we generally assume that there's no effect on the pressure and volume that's there. So the reason why I bring this up is because, yeah, sure, like say you have a container and some particles that are floating around react so that you end up forming a volume or some precipitate or something that collects at the bottom or something. Well, does that occupy volume that's not a gas? Sure. So again, even though the container is actually 1 liter and technically some of it's the solid that's not really a gas, so technically you might be 0.9997 liters actually available for gas. Okay, sure. But again, assumption is that it's still 1 liter. We don't have to worry about those minute details. Also worth noting, gas stoichiometry very much relies on balanced chemical equations and mole quantities, just like every other kind of reaction. So pretty much stoichiometry at this point is the same, except now we have to worry about gas calculations. So in the same way that solutions you have to worry about molarity, gases you kind of probably use a lot of PV equals nRT. Generally speaking, your strategies for this is, of course, to identify the reaction equation. Nothing new there. Make sure that you use your mole amounts as much as possible because, just like we saw in any other unit, the mole amount is effectively the main thing that we use to compare. And so if you do see amounts that are not in moles or see some other quantities of measurement like pressures and volumes, you're going to want to go ahead and use mole amounts as much as possible using the ideal gas law. Right, and we're assuming that all gases behave ideally, so we can just stick that in there and do fine. Perform the stoichiometry as necessary with whatever mole amounts you have. So if you need to limit your reagent, if you need to do some general stoichiometry, use mole amounts. And then finally, as necessary, use your PV equals nRT as necessary to get it back into whatever quantity it is that the problem is asking you for. And of course, to help you simplify work, use those molar volumes, right? If you have STP, that's a magic set of 3 letters, which helps you simplify a lot of your work because you can just relate volumes and mole amounts. It makes it that much easier for you. Let's go take a look at one example here. This is going to be a problem involving something called quicklime, which has a chemical formula or a chemical name of calcium oxide. It's produced by the thermal composition of calcium carbonate. And carbon dioxide is also a byproduct. So if 152 grams of calcium carbonate is decomposed, what volume of carbon dioxide at STP will be produced? Okay, so for this problem, of course, as always, we go through the procedure of identifying the balanced equation if possible. This one, we're starting with calcium carbonate, thermal decomposition of calcium carbonate, which has the formula of CaCO3. And so we're talking about thermal decomposition. We know that it's going to be breaking down. There's no other reactant. We also know that it's a solid because, well, it's an ionic compound. Ionic compounds are generally considered solids unless they're dissolved. And when you have this breaking down, you produce calcium oxide. That's CaO. Once again, also a solid because it's an ionic compound at room temperature. And then you end up forming CO2 as a byproduct CO2 gas. So at this point, we have a balanced chemical equation because, luckily enough, the coefficients are all 1 for this, for it to be balanced. And then the question then asks, if you are given 152 grams of calcium carbonate to be decomposed, what volume of carbon dioxide, STP, will be produced? All right, so we're being asked about the volume of carbon dioxide. The volume of carbon dioxide, of course, is dependent on how much calcium carbonate breaks down to generate the carbon dioxide. So they're asking about information about CO2, while giving me information about CaCO3. So thankfully, we have a balanced chemical equation that we can do that with. 152 grams, that's not 152 grams of CaCO3. Right. Of course, we want to relate 2 different substances, but we have to use coefficients, the mole amounts, and we can't do that using the mass here, so we got to figure out the molar mass. So it's going to be 100.09 grams of CaCO3. Of course, you can find that from the periodic table. And that's going to be equivalent to 1 mole of CaCO3. We have mole amounts of CaCO3 from this conversion. So again, we use a mole-to-mole relationship. So for every 1 mole of CaCO3, that will produce 1 mole of CO2. All right, just good old stoichiometry. So at this point, I would pause here for a moment and try to figure out how we get from moles to volume. Normally, of course, we'd use PV equals nRT because that works for just about every application. But again, we see the magic word or the magic phrase here, STP. So one relationship that we can use is that for every 1 mole of a gas at that set of conditions, it will be equivalent to 22.4 liters of that gas. So there you go. You pretty much have a conversion factor for pretty much every step here, and then you can do some math, calculate the fact that you end up getting 34.0 liters of CO2 that is released when you decompose that mass of calcium carbonate. So again, gas stoichiometry really isn't so much different than the other kind of stoichiometry you've seen in the past. Example 2 here, you notice you have the prompt starts off with some compound sodium azide. Once again, it seems like it decomposes explosively to form sodium metal and nitrogen gas. What mass of sodium azide is necessary to inflate a balloon to 70.0 liters in a room at 25 degrees Celsius and an atmospheric pressure of 0.990 atmospheres. Okay, so the idea here, again, we have some container, there's some sodium azide stuff sitting at the bottom. It's going to explode, right, and generate sodium metal and nitrogen gas. At the same time, it's going to fill up a balloon at a certain set of temperatures and conditions. And so the question is, with all the gas that's generated, right, all the gas that's generated from this combustion, or for this explosive decomposition, what amount will cause you to be able to inflate it at that pressure and whatnot. So let's see what happens here. First of all, again, as always, got to figure out the balanced chemical equation. Sodium azide has a formula of NaN3. It's a solid. It's an ionic compound. And that's going to decompose into sodium metal. And that's going to be a solid. And nitrogen gas, which of course is diatomic, so it's got to be N2. Balance that guy, and you should be getting coefficients of 2, and of 3. All right, got to balance the chemical equation, so let's go and put some work to this. We know we have some volumes and whatnot, so we know we need to generate some amount of N2, and we got to figure out then how much sodium azide it takes to do so. Well, kind of got to work backwards a little bit, because this time we're given a goal of producing some gas that fills up this balloon. And so that means we got to know how many moles of N2 it takes to fill this balloon up with these conditions of 70 liters, 25 degrees Celsius, and 0.990 atmospheres. Now, since we're talking about inflating a balloon, right, and we're talking about atmospheric pressure, well, that means we got to know that the internal pressure here is also going to be 0.990 atmosphere as well, right? Because remember, a balloon is not going to inflate or deflate if the pressures on the inside and the outside are the same. So we're assuming that after this is inflated, the pressure on the inside and the outside are the same. So that means inside the balloon, when we do this work of PV equals nRT, the external pressure of 0.990 is the same as the internal pressure. So let's go start plugging some numbers in as necessary. 0.990 atmospheres times the volume, which is 70.0 liters, is equal to N, which we don't know, R, which is your gas constant, and then temperature, which is going to be 298 Kelvin. Okay, so of course you can plug in R and so on and so forth, and then solve for N. So this tells me how many moles of N2 gas will be necessary to fill up the balloon in that way. All right, so solve for that, you get 2.98 moles of N2. Just kidding, I can't read. 2.83 moles of N2 are necessary to fill a balloon in this way. So if we know we need 2.83 moles of N2, that means we can kind of figure out then, going from N2 back to NaN3, how exactly you need to go. So in this case, I want to set up a conversion bridge. I'm given information about one, I got to figure out information about the other, and then I got to get the gram amount, right? Because that's for how many grams, what mass of sodium azide. So it's going to start off with 2.83, that's a terrible 3, 2.83 grams, no, 2.83 moles of N2. We know that for every 3 moles of N2 that is produced, it requires 2 moles of NaN3, sodium azide. And we got to put in the molar mass to get it from mole amount to mass amount. NaN3 for every 66.02 grams of NaN3. Right. Now, this again is pretty much a setup just like we see anywhere else, regardless of gases and whatnot. And then you do some math, you find out that you needed 125 grams of NaN3 that you need to decompose very quickly in this case, to form enough gas particles of N2 to inflate the balloon to the volume and temperature and pressure that the problem requires. So that's effectively it. You guys have some stoichiometry problems involving gases, and it operates the same way as before. Of course, if you're ever given some problems that involve limiting reagent and such, again, that's the same principles. Figure out how many moles that can be produced from each reactant, and then do work from there. All right, that'll do it.